All right, everyone, it is 8 o'clock, so we are going to get started with the very first of 4 today groundwater-surface water interaction oral sessions. So you will be stuck in this room at the far end of the or the conference center for the entire day, hopefully, with us. Not stuck. You have the privilege of being here all day, yes. So we're going to start out this morning with one of our invited speakers. I'm pleased to welcome James Stegen from Pacific Northwest National Lab. And he's going to be telling us about the influence of dam operations on groundwater surface water mixing zones and multi-scale understanding. So, James, please.
All right. Thanks a lot for the invitation. Thanks everyone for showing up on this early morning, the first day. Exciting to kick this thing off. So, as was said, we're talking about dam operations and mixing zones, impacts of dam operations and mixing zones, and really laying out a framework for multi-scale understanding. I want to call out Amy Goldman and Jerry Tagestad had really important contributions to this talk, as well as the broader Wonders team. You may be curious about what that is. I will tell you about that towards the end of the talk. So let's dive in a little bit. When I'm talking about dam operations, I'm really talking about hydropeaking. And hydropeaking occurs when a hydro dam really induces a lot of high-frequency stage fluctuations and dramatically changes the hydrograph as shown here. Upstream of a dam, normal hydrograph, downstream of a dam, you have these very high-frequency stage fluctuations that are imposed on the system. So the question is, what is really the impacts of that on, in particular, hydrogeochemistry? But here's 4 takeaways that we're going to go through in this talk. First, I'm going to talk about hydropeaking itself and make the point that it's local, it's global, and it's non-uniform at all spatiotemporal scales. In addition, historically, we focused on the ecological impacts of hydropeaking, not so much the hydrogeochemistry and mixing zones. But we are learning things. I'll just mention a couple bits here. One is that the impacts are nonlinear. We've seen that in the literature. But in addition, we do lack mechanistic understanding, in particular on the biogeochemical details. So I'll give one example of that. And at the end, I'll lay out the idea and the framework of how we can go from local to global scale understanding of hydropeaking impacts on hydrobiogeochemical function. So let's dive into this first takeaway message here, hydropeaking itself. Let's go to the local scale. Get Washington State in the background. Zooming into the Hanford site, you can see the Columbia River. You can see a dam right here with an impoundment upstream of it. About 100 kilometers of hydropeaked reach. So what does hydropeaking look across that domain? This plot here is going from upstream to downstream. Time is on the x-axis. The colors indicate the intensity of hydropeaking, how variable the river elevation is through time. So you can see is that the hotter colors are higher intensity of hydropeaking. The point is not to get into the details of this. The point is through space and time, the level of hydropeaking itself is extremely variable. So that's the local scale. Let's go to the global scale and just make the point that globally, hydro dams exist all over the world, but their density varies dramatically. Higher or sort of hotter colors, higher intensity of red, indicate higher densities of hydro dams, up to almost 70 per square. Totally lost my train of my wording there. It's 1 degree grid cell. Sorry, square 1 degree grid cell. So the point is, hydropeaking itself is local, it's global, and it's non-uniform. So now the second take-home is that historically we focused on the impacts, more on the ecological impacts, not so much the hydrobiogeochemistry. So to show this, we went through the literature and found over 500 papers looking at hydropeaking in some one respect or another, took the abstracts out of that, ran those abstracts through a clustering program that does a text-based analysis called INSPIRE. From that you can do multivariate clustering and visualize that in a principal component analysis, which is shown here. So this is the first 2 principal components, doing a text-based analysis. The height of the peak is the number of papers falling in that particular area of multivariate space. And what you see is all these big peaks here in the corner, that's basically fish and invertebrate ecology, primary producer ecology. There's some minor secondary peaks about some physical processes, mitigation of hydropeaking, certainly some work being done on mixing zone hydrology. When I look at that figure, what I'm not seeing is a big peak about biogeochemistry, about microbial ecology, microbial function. That's not been a historical focus. And that leads to some real knowledge gaps in terms of what the impacts of hydropeaking are. But we are learning things, of course. And that goes to the next takeaway. In particular, that the impacts of hydropeaking are nonlinear. And I'll make that point here. A study from Chao and Fleckenstein earlier this year, you get hyporheic zone nitrate consumption relative to input as a function of cumulative discharge. So you can see these nice relationships across a few different scenarios. But what's important is this box down here. You can see these horizontal dashed lines. In those places, those data points are coming from conditions where discharge is below a specific threshold. In this case, I believe it was 1.2 meter cube per second. And if you're below that point, below that discharge level, there's no influence of hydropeaking on biogeochemistry. You have to move beyond that threshold to see an impact. So the point is the effects are nonlinear. But as I was mentioning, we are learning things, but there's still a great need for more detailed mechanistic understanding, in particular on the biogeochemistry side. I'll make that point here using an example from the system we study, which is the reach of the Columbia River that I showed you previously. We have good end members in this system. We can look at groundwater in black, we can look at river water in blue, and this on the vertical axis is dissolved organic carbon concentration. The x-axis is a groundwater fraction. The red points are in the mixing zone. And what you see is we have a linear mixing model, and we have strong deviations from that mixing model. We have much less organic carbon than we should based off of a linear mixing model expectation. You can look at dissolved inorganic carbon, same samples, same setup, groundwater, river water, those deviations are falling above the line. You can relate those deviations to each other, and as you go to the left on the x-axis, you're losing more organic carbon relative to the expectation. On the y-axis, you're gaining more inorganic carbon relative to the expectation. That's indicative of stimulated respiration in the mixing zone. But what's interesting in this system is that both end members are aerobic. Groundwater is aerobic, surface water is aerobic, and so it's sort of the classic thinking and paradigm of stimulated activity in the mixing zone being due to bringing together complementary electron donors and acceptors doesn't really work in this system because there's always oxygen. We always have an electron acceptor. And so we've conceptualized this in a different way where the groundwater in this system, low concentrations of organic carbon, but each molecule itself is readily accessible for microbial oxidation. But it's constrained by that low concentration. In the river water, higher concentration of organic carbon, but each molecule is not very accessible. So each of those end members is limited by a different factor, a different mechanism. And when you bring them together, changes in the organic carbon speciation and profile is actually stimulating activity. So this is kind of a different view, a different mechanism that kind of adds to the idea of mixing zones and what's driving their biogeochemistry. And we have field data I'm not showing you that's consistent with this conceptual model. And Vanessa Garbaru-Caroso will talk a little bit about this later today in this session at 3:25. I encourage you to go there. And so let's sort of step back and hit these takeaways again. Hydropeaking, as I was showing you, it occurs locally. It's highly variable through space and time, both locally and globally. And there are important knowledge gaps. We're gaining understanding in terms of the hydrobiogeochemical impacts of hydropeaking. But there's a lot we don't yet know, in part because historically we focus more on ecological impacts, not so much mixing zone hydrology and biogeochemistry. We are making advances, but there are still gaps in our understanding, in particular some of the detailed mechanisms on the biogeochemistry side. And so when I look at that, I see a really important problem, a global problem that's growing. More and more hydro dams are being built. There's key knowledge gaps, a really heterogeneous system. How do we gain synthetic, consistent, global understanding that can go from local to global scales? And what we're doing is we're launching something that we call WONDERS. WONDERS has a long name, Worldwide Hydrobiogeochemistry Observation Network for Dynamic River Systems. Just remember WONDERS. And the one point here is that the name of this does not include hydropeaking, right? I've been talking about hydropeaking, but WONDERS is going beyond hydropeaking to any system where we have sustained high-frequency stage fluctuations. That includes tidal river systems, hydropeak systems, even Great Lake systems, glaciated systems. There's a lot of different kinds of systems that have that kind of sustained high-frequency stage fluctuation. And there's a lot to learn there. And so the idea of WONDERS is to be a global consortium of researchers that are studying the hydrobiogeochemical impacts of, as I was saying, of high-frequency sustained stage fluctuations. And the map here is the same map I was showing you before. In terms of the colors, I've added on the location of about 100 studies that have looked at hydropeaking impacts on some aspect of river corridor ecosystems. And the dream of WONDERS is to have a footprint, to have in all these types of locations across the world, using consistent methodology and consistent instrumentation and modeling approaches to be able to go from those local scale, site-based understanding to broad global scale phenomena. And to that end, WONDERS is really aiming for transferability of site-specific knowledge throughout the world, as I was saying, using consistent methods, ultimately to improve predictions of river corridor function. And the idea of WONDERS is to enable the research community, in particular this research community, to globally and consistently pursue mechanistic understanding of hydrogeochemistry in these mixing zones as a consequence of high-frequency stage fluctuations. And so WONDERS, as a consortium, this is sort of the launch right here. We're just getting going. And there's a website, I'll put this on the next slide as well, so you don't have to write it down yet. But WONDERS, as a consortium, hinges on collaboration. We're really hoping people can reach out to us. And some thoughts about what is useful to you is in terms of joining WONDERS. What does being a WONDERS partner actually get you? Well, for one, sort of intrinsic interest in joining a global effort to understand hydrogeochemistry in mixing zones. Share your locally gained understanding and knowledge with the broader community. All data generated through WONDERS will become publicly accessible. We'll host that data to understand how each system is fitting into the global picture. In addition, WONDERS partners have access to new sensor technology that we're developing. So this here is just a graphic of that. An example, it's a multi-parameter vertically distributed sensor system that we're working on developing right now. WONDERS partners will have access to that new technology, as well as we're partnering with the Environmental Molecular Sciences Lab, which is a DOE user facility on our campus. We'll be supporting high-resolution carbon characterization across globally distributed systems. So with that, what I want to do is end by mentioning we have a lot of internal PNNL partners. We also have a number of external partners that are excited to be on board. I've indicated some of their presentations throughout AGU. Our funding comes from DOE, in particular subsurface biogeochemical research. So as I was saying, WONDERS hinges on collaboration. We're really hoping people will reach out to us here at AGU and beyond. We have a presence on a number of platforms. That's our website, Twitter handle, LinkedIn group. You can send an email, whatever works for you. Now, really hoping you can reach out. Thank you very much. Take any questions.
It's over. All right, we have plenty of time for questions. Anyone like to start us off?
James, I want to start with a question for you, and it is regarding the maps showing like where dams are on this planet. So we see a lot of red on the north, right, US, Europe region, and then some numbers down in South America and Africa. So as a person from Colombia, knowing that building dams is kind of a new thing, right? How do you expect to transfer information from, sites like the U.S. where we are removing dams day after day to sites in South America where the goal is to build dams to generate electricity and et cetera?
Yeah, so the idea of WONDERS is to deploy consistent instrumentation and use consistent methods across a very broad range of systems in the U.S. and across the world to gain really synthetic understanding of how fine-scale mechanistic processes scale up to impact river corridor function broadly. And the idea is if we can have that fundamental understanding, trying to use that knowledge to at least inform what the likely impacts might be when installing new dams and how one might operate those dams to at least minimize any negative effects or operate them in ways towards beneficial outcomes. There is potential, at least in moderately sized systems, to operate dams in ways that can actually improve water quality by enhancing hyporheic exchange. And so the idea of WONDERS is to provide that broad-scale mechanistic-based understanding for broadly informing decision makers ultimately.
Great. Thank you.
Okay.
Another question? Yep.
We talked a lot about consistent methodology. What do you see kind of as what are the major things you're already measuring, and what do you see, what will be the next couple of things you'd like to add to that package?
Could you paraphrase?
Yeah, so the question was, what are we currently measuring and what do we want to add? So we could talk for a long time about that. Briefly, I'll just mention this sensor technology. So one of the key things is to estimate hydrologic exchange flows between surface water and the hyporheic zone. In these very dynamic systems, it's actually very challenging to do that. People have used vertically distributed temperature to do that in more steady state systems. In very dynamic systems, that doesn't really work. It's not enough. And so here, we're getting vertically distributed temperature, pressure, fluid conductivity, bulk conductivity, and porosity to get that exchange flow, all in one very streamlined sensor rod that can do all that, in part using geophysics as well as built-in sensors.
Thank you, James.
Thank you.
So we're going to move on to our second speaker. Alrighty, so our next speaker is Kaylyn Gootman from North Carolina, Chapel Hill, and she is going to talk about my favorite subject at the moment, using reactive tracer tests to model solute transport in montane river continuums. Is this?
Yeah, it should be good. Okay.
It's our first Mac PC transfer. There we go. All right, so please take it away. Laser pointer. There we go.
And then to advance is probably
that, or we can do that as well. One of those work?
Yeah. Great. Perfect. All right. Thank you so much. All right. So in thinking about hyporheic exchange studies over the past 30 years, the majority of those studies have taken place in headwater streams, so streams that are first, second, third, or even fourth order streams. And out of those studies, there's a large percentage that I've highlighted here in red that have been completed in first order streams. So this makes sense. These are smaller parts of our river systems that are easily construed and a bit easier to study. But what we're really curious about is how does this reliance on these small streams impact what we know about river systems? Does this create knowledge gaps in our understanding at larger spatial scales? So, as a part of our study, we were interested in looking at the first 5 stream orders of a river system to really investigate 2 different components of hyporheic zone processing, reactivity and residence time. And how do these change across spatial scales, and in this case, meaning stream order? So we know with river systems, we've got different physical aspects and different things that change spatially when we increase stream order. Obviously, flow increases as we move from small to larger stream orders, but there also is a trend where we've got an increase in turbulence, a decrease in submerged aquatic vegetation, and increases in sediment loads. So we were really curious in thinking about these spatial variabilities, also what's happening temporally. So our goal was to quantify hyporheic zone residence time and reactivity across different stream orders to understand this variability in processing that's occurring. So to do this, we completed instantaneous tracer injections in 5 different stream orders along the Jemez River, which is north of Albuquerque, New Mexico, and a major tributary of the Rio Grande. So at each of our sampling stations, we had a co-injection where we injected bromide, a conservative tracer, and rizazirin, a reactive tracer. And at each site, we had 2 downstream sampling stations. We sampled our surface waters for bromide, rizazirin, and its daughter product, rezorufin. Previous studies have shown that the transformation, which is irreversible, of rizazirin to rezorufin is a good proxy for aerobic respiration. So within our study, we went in 2 different sampling years, in the summer of 2015, which is shown in this light blue box, and in the spring of 2016, which is shown in dark blue. And it's interesting to note, or good to note, that in our summer sampling season, this was completed during base flow conditions that were typically drier for the region. And in our 2016 sampling season, this was at the end of the snowmelt period for the region and had typically higher flows and wetter conditions. And it's also important to note that in 2016, we were only visiting the first 4 stream orders. And for the remainder of this talk, any data or results in light blue will be from 2015, and in dark blue will be from 2016. So once we completed our tracer injections and had our data, we applied a one-dimensional transient storage model that has been previously used by Knapp et al. 2017 to couple surface water reach processes with our hyporheic zone. So we used a variety of variables within this model to generate our parameters. And so after getting our data using our model, the outputs were simulated breakthrough curves for each of our 3 tracers. So on this plot here, on our left-hand axis, we have bromide in moles per meter cubed. And bromide and its measured points and simulated breakthrough curves are in black. And on our right-hand axis, we have the concentration of rosazurin and resomurifin in moles per liters, and those are in blue and red respectively. And we can see here we have our instantaneous injections in our upstream and downstream locations. So taking our model and our simulated curves, we can then get different results that we're interested in knowing more about when it comes to hyporheic zone processing. So the 2 results I'm showing you here are mean hyporheic zone residence time on the left and reaction rate coefficient on the right. And when you're looking at each of these results plots, our x-axis is increasing stream order, and our y-axis is the variable or result of interest. So in looking at mean residence time, which is in seconds, we can see when excluding the first stream order, in our dry year, which is light blue, 2015, we have a trend of a decrease in residence time with increasing stream order. Now it's interesting, in our wet year, we have the opposite trend. When looking at streams not in the first order, we have an increase in mean residence time. Now looking on the right at our reaction rate coefficients, our first stream order had pretty similar reaction rate coefficients, and in our dry year, 2016, subsequent stream orders had about the same reaction rate coefficient, whereas in our wetter year, they were more variable. So in thinking about these 2 results, residence time, reactivity, we wanted to use a way to relate the 2. So one way to do this is to use the reach scale Domkohler number, which is taking the residence time and the reactivity. And you can think about this as actually a ratio or a way to describe the relationship between transport timescales and reaction timescales. So when plotting this unitless Domkohler number, where we have our x-axis is stream order and our y-axis is Domkohler number, we can think about the different values we get and what that means for hyporheic zone processing. So anywhere where a Domkohler number is greater than 1 means the hyporheic sediments are transport limited. Anywhere where there's a Domkohler number that's less than 1, we have a system that's more reaction limited. And anywhere where a Domkohler number is equal to 1, which is indicated by this dashed line, is where there's a general balance between transport and reaction limited components, meaning theoretically, this hyporheic zone could have the greatest ecosystem service benefit because a balance of transport and reaction limited timescales theoretically support a maximal hyporheic flux. So now here's some data. So again, our light blue is our dry season and our dark blue is our wet season. So looking at these data from these 2 different years, we can see there's similar patterns between both sampling seasons, whereas our first order streams are clearly in the transport limited region, and the following stream orders in both years are either reaction limited or balanced. So the takeaway point here when looking at Domkohler numbers in this manner is that our first order streams and those results really aren't readily transferable to our higher stream orders. So another way to think about Domkohler numbers and this relationship between reaction timescales and transport timescales is to plot them in an XY space. So here on our x-axis, we have the hyporheic residence timescale in hours, and we have the reaction timescale in hours on the y-axis. So again, looking at how our Domkohler numbers would fall on this plotting space, again, our first order stream section in our dry year is in the transport limited region. But what's interesting to look here, and what I think this plot really shows, is the spatial variability when you're changing to a higher stream order. So we move from our first order stream that's transport limited to our second and third order streams, which are now seemingly more balanced when it comes to our Domkohler number. And our higher stream orders, the fourth and fifth stream orders, are now in the reaction limited space. So when looking at data from our next sampling year, which was our wetter season in 2016, we have something that also shows a driver of spatial variability, but the opposite pattern is happening in our higher stream orders. Our first order stream is still transport limited, but now our second and third order streams are reaction limited instead of being balanced. And in our fourth order stream, we have balanced conditions as opposed to reaction limited. So it's really interesting to see we've got the spatial variability or spatial drivers of hyporheic zone processing that we can see in 2 different years. But it's also interesting to think about the temporal aspect or seasonality that's occurring. So it seems that seasonality is a major driver outside of our first order stream, where we have clearly transport limited conditions in both seasons. But there's this interesting dynamic that occurs in our higher stream orders where the wet or dry conditions or the type of season create this kind of switch. So to sum these results, it's really interesting to think about the Jemez River system and its net functional behavior, at least in the hyporheic zone, is both spatially and temporally dynamic. So if our first order streams are small and consistently remain transport limited, our second and third order streams, when going from dry to wet conditions, really shift from balanced to reaction limited conditions. And in our fourth order streams, we have the opposite switch here from reaction limited to balanced. So in thinking about the Jemez River and kind of that question that I had earlier on in the talk, what's going on in our first order stream section is not really readily transferable to higher stream order sections. And this poses an interesting question or point when it comes to where we sample and at what point or what parts of the rivers do we study when we're selecting our sites. If we were to have only gone to fewer stream order sections or only sampled in 1 year, we may have missed the temporal and spatial variability that's been going on within the system. So where we sample and when we sample really does matter. And so in thinking about this, there's these dynamics going on and these dynamic processing, where we can't assume that the hyporheic zone is a static thing that does the same thing at all the time. And in thinking about the dynamics and kind of beyond just this one river system and hyporheic zone processing, it's really important to not only think about where it's happening, what's happening, but also why is there this variability? Why does this variability exist? Now, this isn't something that we can answer just looking at this one river system. But in thinking about ways to utilize data that we already have, so not saying we must sample more, we must collect more data, that's important too, but really trying to think together as a field, why are there these, variabilities? What is going on? So a potential way to do that might be to create a framework that's using these kind of descriptive metrics, such as Domkoehler numbers, along with our known stream characteristics, to try and come up with a framework to better explain why is this variability occurring, and trying to fill these knowledge gaps in these higher stream orders. So in this example here, I'm just showing a framework where we have temporal variation, spatial variation, and additional stream characteristics. We have some insight into what's going on within these first through fifth stream orders, but we still need to fill in these knowledge gaps. So perhaps a way forward for the field is using some kind of conceptual framework that helps get at why we have this variability, and using data that we have, those unique contexts for those stream systems, and really trying to get at together why are we experiencing these kind of variabilities. So with that, thank you, and I'll take any questions.
All right, thank you. So we have time for one question as we switch speakers. Yes?
I noticed, so you had high dam flow numbers for your first order streams and everything else was a lot lower. I sort of expected that to be driven by shorter residence times, but it seemed like that wasn't really the case. Do you have any thoughts about why the reaction rates were so much faster in those streams?
Yeah, it might be, so our first order stream section was a really narrow stretch of stream, and we had actually a lot of what we could actually see one sampling season we were out there. There was actually a lot of dilution occurring. So we had a lot of other water inputs coming into the stream. And so that might be the answer as to why. So thank you.
All righty. Thank you.
Thanks, guys.
Thank you. Thanks, guys. So. Okay, so our next speaker is Morvarid, sorry, you just told me up. Azizian from UC Irvine, and she is going to be telling us about ambient groundwater flow and its effect on diminishing nitrogen cycling in streams. And switch it over. Yeah, it's easy. So we have a pointer, and you can change with it. Perfect.
Hello everyone, good morning. Thank you for the opportunity. So my name is Morvarid Azizian. I'm a postdoctoral researcher at University of California, Irvine. And I'm going to present this recent study from our research group. This has been possible by the contribution of all the great co-authors that I had on this paper, which was published in Water Resources Research recently. So I'm going to talk about the effect of ambient groundwater flow and how this basically diminishes nitrogen cycling in the streams. So as we all know, in-stream processes provide enormous ecosystem services to aquatic ecosystems, such as nitrogen removal. And previous studies have shown that exchange processes across the submerged bed forms, such as riffle pool sequences or ripples, have huge implications in terms of the hyporheic exchange fluxes and turnover of nutrients along the river corridors as opposed to the lateral exchange processes through the meanders. In addition to the bed form type, the stream flow regime and also groundwater discharge and recharge can alter the rate of hyporheic exchange and also chemical processes in the system. So our research question for this study was to basically see how nitrate processing in the streams can be affected by the combined influence of the hyporheic exchange across ripples and also riffle pool sequences, how this is going to be affected by surface water, groundwater interactions in gaining and losing streams, and also what is the effect of a stream flow regime in terms of nitrate removal in hyporheic zone. In order to answer this question, we implemented a previously published mechanistic model, process-based model called Pumping and Streamline Segregation Model, or PASS model, which was based on four simplifying assumptions. One, the main one is that we assume that the transport of water through the sediment happens through a bundle of hyporheic zone tubes, which they have no mixing, there is no mixing across these hyporheic zone tubes, and all the dominant mechanism of mass transport is advection, not diffusion and dispersion. And also we considered a steady state condition. So in order to calculate the uptake velocity of nitrate, we knew that the nitrate removal depends on the exchange of water, basically flow rate of water through the sediment, which we call it hyporheic exchange flux. And also it would depend on how much nitrate is taken up by the sediment, which we represented by the ratio of exit concentration of nitrate that is coming out of the sediment divided by in-stream concentration of nitrate. And in order to calculate the uptake velocity, we basically combine all these together and calculate uptake velocity as the benthic nitrate flux divided by in-stream concentration of nitrate, which is represented by this equation. And in order to calculate exit concentration of nitrate, we basically calculate or derive concentration evolution of nitrate along the hyporheic zone tubes, which is a function of the residence time associated with each hyporheic zone tube, and convolve this with a residence time distribution of all the hyporheic zone tubes, and finally integrate over all possible residence times of hyporheic zone tubes. Therefore, our process-based model boils down to three simple steps. One is to define what is the hyporheic exchange flux, how is the residence time distribution, and the last one is to derive the concentration evolution along the hyporheic zone tubes. So for the first part of the analysis, we calculated the hyporheic exchange flux for different hydrological scenarios. For ripples case, we we utilized the characteristics of the ripples scenarios that were used in a Flux et al. 2014 paper, and for ripple pool sequences, we utilized the characteristics of the ripple pool sequences that were used for Throth et al. 2013 paper. In addition to that, we adopted the same conditions in regards to the hydraulic conductivity, porosity, and the slope of the stream, consistent with Throth et al. 2013 paper. And also we used 10 ambient flow scenarios in regards to the stream flow discharge, including high discharge versus low discharge, as well as 5 different groundwater scenarios, including 2 gaining scenarios, 2 losing scenarios, and 1 neutral condition. Our results are presented here, the hyporheic exchange flux versus the different values of groundwater vertical flux, color-coded with respect to the stream discharge, and also differentiates for ripple pool versus ripple scenarios. As you can see here, although the ripples are smaller features, they tend to have higher hyporheic exchange flux, going from 3 to 11 times larger than ripple pool sequences. Also, we could see that the hyporheic exchange is larger for simulations that were conducted at higher stream discharge, and also hyporheic exchange declined with increasing groundwater flux. The second step was to identify the residence time distributions for each of these hydrological scenarios that we considered. And for the ripple pool sequences, under gaining, losing, or neutral conditions, we implemented the residence time distributions that were derived in Throth et al. Computational fluid dynamics model. And for ripples, we derived new analytical solutions based on Elliott-Brooks pumping model and Buono's 2008 study. And basically, we modified that solution, analytical solution, in regards to groundwater effect. We found that ripples have a peak residence time about 5 minutes, which was much less than ripple pool sequences that had 3 hours peak residence time, but also ripples have very long power law tail, which had a huge implication in terms of nitrogen cycling in a sediment, which I will explain in the future slides. Also, we could see that increasing groundwater flux, as you can see here, going from darker shades to the lighter shades, reduces peak residence times and truncates the tail of the residence times. Also, increasing stream discharge shifted the residence time distributions to the shorter times. The last step was to define how nitrate is going to evolve along each hyporheic zone tube. And in order to model that, our model, biogeochemical model, accounted for 4 biogeochemical reactions, including aerobic respiration, denitrification, nitrification, and ammonification. Therefore, we needed to specify the reaction rate constants for these 4 reactions, in addition to mineralization rate of organic matter, as well as in-stream concentrations of oxygen, nitrate, and ammonium. But we knew that the in-stream concentrations of oxygen, nitrate, and ammonium and organic carbon tend to co-vary across different streams, and they are not statistically independent. Therefore, in order to parameterize these quantities, we knew that we have to account for these covariance. In order to have realistic concentration values and mineralization rate constants, we implemented links to data set, which stands for Second Lodic Intersite Nitrogen Experiments, and ran principal component analysis, PCA, to select 3 stream sites that could collectively capture the diversity of the biogeochemical setting of the stream from pristine to polluted condition. And when we did that, we selected 3 streams, which the first one was NCC in North Carolina, which corresponded to a pristine stream. And the second one was a stream in Puerto Rico, which was highly urban impacted stream. And the last one was a stream in Kansas, which was an urban impacted stream. And as you can see here on this plot, we have nitrate concentration, which is remaining in hyporheic zone tube, normalized by in-stream concentration of nitrate. And the horizontal axis represents the residence time in the hyporheic zone tube. And when we have lower values of residence time, there is not much enough time for biogeochemical reactions to remove any nitrate. Therefore, nitrate concentration in hyporheic zone tube is going to be equal to in-stream concentration of nitrate. Therefore, its value is going to be close to 1. And as the residence time increases, the concentration of nitrate in hyporheic zone tube due to nitrification processes increase, and depending on the respiration time scale of the biogeochemical scenario that we are considering, the concentration of nitrate will fall below the in-stream concentration of nitrate. Therefore, sediment would act as a sink of nitrate. So now we have all three components of our modeling framework. Therefore, we can quantify nitrate removal by hyporheic exchange. So we combined all these components and calculated optic velocity. I'm presenting the total optic velocity here for three scenarios with respect to different groundwater scenarios, and also the color codes are the same as previous plots that I presented. As you can see, all of the scenarios represented sediments as a source of nitrate because the VF optic velocity was positive. And we saw that nitrate cycling was almost always larger for higher stream discharges and also higher in refill pool sequences, and would decline as groundwater flux increases. And in addition to the optic velocity, the total optic velocity, we also calculated optic velocity due to coupled nitrification, denitrification, as well as direct denitrification of in-stream nitrate. And I'm just presenting the results for direct denitrification, which was reported in Mulholland et al. 2008 paper, which was basically as part of the Links 2 studies. As you can see here, the stars represent the actual values that were reported for the three biogeochemical scenarios that we considered. And these are all the values that are reported for direct denitrification versus concentration of nitrate in a stream. And the symbols present our model predictions for each of these scenarios. The main point of this comparison was to understand whether our model can estimate the direct denitrification optic velocities in a good way or not. And we found that basically our model can have a good estimate of this optic velocity. So as a conclusion, our process-based model provided an easy way to evaluate how multiple interacting exchange scales influence nitrogen processing in the streams. And our model provided a realistic estimates for direct denitrification. However, due to several reasons, our model overpredicts nitrification and coupled nitrification, denitrification. We could show that fluvial ripples generate up to 11 times more hyporheic exchange flux than refill pool sequences, but refill pool sequences have are dominant in nitrogen cycling because of their longer residence times. And also the main conclusion was that vertical groundwater flux modulates both hyporheic exchange flux and relative rates of organic carbon mineralization and advective transport in the streambed sediments that is presented as damp Kohler number, as we saw in previous presentation, and tend to diminish nitrogen cycling in the streams. And also an important implication of this conclusion is that by changing groundwater hydrology that can be brought on by climate change or overpumping, we can affect hyporheic zone function and also the provision of these ecosystem services such as removal of stream-borne nitrate. This study has been published in Water Resources Research and has been selected by US Spotlight, so you're welcome to have more information from both of these articles. And with that, I'm opening it to further questions. Thank you very much for your attention.
All right, we have time for a very short burning question while we switch speakers. Otherwise, we're fine. Okay, Stefan?
Right, thank you very much. I found your one-word last conclusion a bit difficult. If I understand you correctly, you parameterize your groundwater just as a physical force, right? Your groundwater has no loading. There's no nitrogen coming in. You use examples, for instance, from North Carolina, where your groundwater is one of the major nitrogen sources.
Yes, exactly, yeah. No, we didn't consider nitrogen source from groundwater. So the only source of nitrogen in our model is from stream nitrate, and that's one of the limitations of our model currently. It's just a physical force groundwater component.
So you plan to change that, or?
Yeah, it could be improved in the further. Yeah, definitely. Thank you.
No, that's good. All righty, thank you very much. So we're going to move on to our next speaker, Molly Welsh, who is working with Philippe Vaidon at SUNY ESF, and she's going to be telling us about cross-vein restoration structures and their impact on riparian zone hydrology. So, Molly.
Great. Well, thank you to everyone for being here today, and thank you to the conveners and chairs for hosting this session. My name is Molly Welsh. I'm from SUNY ESF, and I worked with Philippe Vaidon and Sarah McMillan on this project. And our funding sources were USDA and the National Science Foundation. And I'll be speaking about cross-vein restoration structures and more broadly, the impact of stream restoration on riparian zone hydrology. So land use changes, particularly conversion of forested environments to agricultural areas, often lead to aquatic ecosystem degradation. So for example, agricultural streams are often straightened and channelized on the landscape, essentially being transformed from meandering streams into drainage ditches. These drainage ditches often experience incision, erosion, and hydrologic disconnection between the streams and their associated floodplains. And as a result, they often suffer water quality degradation. So in response to these physical impacts on streams as well as the water quality degradation, stream restoration is often implemented in areas all around the globe. And the natural channel design approach that I will be speaking about today involves both elements of stream and riparian zone manipulation. So within the stream itself, cross-vein structures have been implemented, and these are boulder, channel-spanning structures that are anchored in the riparian zone, and they create a riffle, step, pool sequence. So they concentrate flow into the center of the channel to reduce erosion. The riparian zone is often regraded and revegetated, and this is to reduce erosion and also to enhance stream riparian zone connectivity. So because stream restoration is increasingly important in watershed management planning, a lot of studies have investigated the impact of restoration on hyporheic zone fluxes of water and pollutant dynamics. However, even though these studies have shown that restoration structures are able to influence the local hyporheic zone, often by orders of magnitude in terms of downwelling and upwelling from pre-restoration state, the impact beyond this immediate hyporheic zone is often understudied in terms of riparian groundwater flow paths. So I aim to investigate riparian flow paths and function. Further, other types of in-stream impoundments have been shown to alter riparian hydrology. So a study by Westbrook et al. In 2006 showed that not only did in-stream impoundments raise stream water levels above the impoundments and enhance surface flows, they also could lead to increased zones of high groundwater tables. And so you can see here an area of influence within the riparian zone from the in-stream impoundment from the Beaver Dam. So the floodplain restoration approach I'll be talking about today is natural channel design, and I'd like to evaluate how geomorphic changes, particularly installation of these cross-vein structures and regrading, could alter riparian zone hydrology and to what extent. And from previous research, we think that these restoration structures may lead to higher groundwater tables in the adjacent riparian zone. So our field sites were located in the Piedmont region of North Carolina. Our restored site was restored in 2012, and you can see here from an aerial photograph that the stream was not remeandered and the cross-vein structures were installed in this straightened channel, and this is the arrangement of cross-vein structures on the landscape. Our unrestored site is incised and it has a mixed herbaceous forested buffer, and you can see the aerial view from this photograph. And our forested site was located in a state park, and it does have a deciduous buffer. However, there is agricultural activity upstream in the watershed, and this is the aerial photo. So at our field sites, we installed a network of stream and riparian piezometers, which are indicated by the black dots on the graphs you see here. We surveyed the location of these stream and riparian piezometers and also took several cross-sections throughout the riparian zone to get an idea of the topography of the sites. We also evaluated the presence of in-stream geomorphic features, so pools, runs, riffles, and we even have a symbol showing where crossvein created pools became filled in over time throughout our study. And within this riparian zone and stream piezometer network, we took seasonal water samples for 2.5 years at these field sites. And these field sites were also instrumented with continuous loggers for water level and soil moisture. So this is showing the results of the seasonal riparian zone water table levels, and it's displayed in meters below ground surface. And to orient you to the graph, the blue corresponds to the near stream riparian zone area, the brown corresponds to the mid riparian zone area, and the green corresponds to the upper riparian zone adjacent to the agricultural field. And so we found that local geomorphology, which is influenced by restoration, often drives variability in groundwater table depths. So at our restored site, our groundwater depth was often within 0.5 meter of the ground surface in this near stream zone, where this zone was influenced by crossvein installation as well as riparian zone regrading. In our unrestored site, we saw that the riparian zone near stream water table was often greater than 0.5 meter from the water surface. And we saw less of a separation in terms of groundwater table below ground surface between our 3 different zones. And this unrestored site was incised and also had relatively homogeneous sandy loam soils. And then our forested site had interesting geomorphology. One of the wells actually showed groundwater table that was within 0.5 meter of the riparian zone, and this was located near a riffle, but a few other wells showed groundwater levels that were deeper, over 1 meter, and these were located in a vegetated point bar area. Additionally, our mid-riparian zone had a small depressional area, which was often a secondary transient channel, so this had a water table that was closer to the ground surface than some of our near stream wells. And in our upland area, our water table was variable, but we often couldn't measure it because it was often greater than 1 to 2.5 meters from the land surface. So these diagrams show water table contours at our 3 different sites from a bird's eye view as meters above an arbitrary datum, as well as cross-sectional views of hydraulic head showing equipotential lines. So I'd like to start in the middle here at our unrestored site. So at the unrestored site, we generally see a gradient across the valley from the upper riparian zone near the agricultural field to the stream. And we see minimal stream riparian zone interaction, and this is supported by our hydraulic head map. At our forested site, we also see a similar hill slope gradient, and this starts at the depressional area and moves toward the stream. However, we see the influence of riffles on near stream riparian zone groundwater levels. At our restored site, we start to see the development of the gradient from the agricultural field moving toward the stream. However, we hit an area of low hydraulic gradient in the regraded area downstream of the crossvein. And so we've mapped this zone of influence as 10 centimeters above and 10 centimeters below the water level adjacent to the crossvein. And so this is shown here. It doesn't exactly follow contour lines because of our mapping structure. And in the middle of the riparian zone, we see a little bit of upwelling, and this upwelling encounters this zone of low hydraulic gradient, and we start to see a mound forming downstream in the riparian zone. Next, we'll look at water table and hydraulic head under drier conditions at the field sites. So again, this is expressed as meters above an arbitrary datum. At the unrestored site, we continue to see a dominant gradient from the agricultural field toward the stream. The water table depth is a bit different because it's drier conditions, but generally this gradient dominates. At the forested site, we again see this hill slope gradient from the depressional area, And we see the influence again of riffles on our near stream riparian zone groundwater. And then at our restored site, we again see the influence of cross veins and the regraded near stream riparian zone on this area of lower hydraulic gradient close to the stream. And in the summer, we see a small flow reversal next to the stream where water is moving from the stream bank outward, and this is inducing a small down valley gradient in this near stream zone. And though I showed you wet conditions and dry conditions, we noticed that the effect of the cross-vein structures and regrading persisted in terms of the lower hydraulic gradient seasonally. So this is a short video that shows you the 2.5 years of monitoring. So again, we mapped the area of the influence of cross veins as 10 centimeters above and 10 centimeters below the water table level adjacent to the cross vein. Our last hydrologic measure was of groundwater fluxes, and this is in liters per day per square meter of aquifer. And so we saw our restored site had lower groundwater fluxes than our forested site, and we thought this was largely influenced by soil type and geomorphology. So our restored site had clay soil types and was likely compacted from the influence of construction equipment on the riparian zone, whereas the forested site had deep groundwater tables, very sandy soils, and varied geomorphology. So in conclusion, both the restoration process as well as existing geomorphic conditions are important for explaining riparian zone hydrology. The restored site had higher near-stream water tables than the unrestored site, likely due to the regrading that occurred. We saw similar stream riparian zone interactions to the forested site, likely due to the influence of cross veins and regrading. And we also saw that the restored site had lower groundwater fluxes than our forested site, and this was likely due to the soil type and geomorphology. Cross-vein restoration structures have impacts beyond their immediate hyporheic zone. They can alter groundwater flow paths and gradient, and this is similar to beaver ponds. Additionally, the effects of the riparian zone, the effects of the cross veins and regrading on riparian zones persisted seasonally. And this effect was observed even after cross veins ceased to function a few months into our sampling scheme. So this was after plunge pools downstream of the cross vein that were used for erosion control actually filled in with sediment. So natural channel design is a common restoration approach in the United States and Europe, and therefore it has the potential to alter riparian zone hydrologic processes globally. Additionally, it's important to continue to investigate riparian zone hydrology coupled to measures of biogeochemistry, such as nitrogen, phosphorus, and greenhouse gas fluxes, so that we can understand potential pollutant trade-offs. And so a companion study involves investigation of movement and transport of these solutes and gases through the riparian zone and stream. Stream riparian zone interaction may enhance denitrification if you have higher groundwater tables, but this could lead to soluble reactive phosphorus release or release of greenhouse gases. So more research is warranted. Thank you for your attention, and I will be happy to take any questions.
All right, thank you. We have time for a question as we switch over. You want to? Jan?
Very interesting talk. I was wondering, usually the problem with the restoration projects is that there isn't very much post-restoration monitoring of water quality. Are you aware of any studies that have looked at this? Because often it's difficult to evaluate the integral effect, let's say, on nitrate in the stream or phosphorus, because there isn't this data available. You make the restoration, but it's not followed up by additional monitoring. Are you aware of any activities that include those kind of aspects into the restoration projects?
Yeah, I think that it's becoming more common, and there was an effort to put together a restoration database, a synthesis of different restoration studies and monitoring that had occurred. So I know especially since 2005, monitoring of post-restoration, both hydrology in terms of hyporheic zone fluxes and water chemistry has been occurring. There are comparisons that we've made in our sites to other restored urban streams as well as to restored agricultural streams in Midwestern areas, in addition to the Southeast where I work. So there are a variety of studies, and I'm hoping that it's going to become more common in the future as well. Thank you.
Great. Thank you very much.
Thank you, Molly. And the next speaker is going to be Stephen Ferencz, and he's going to present on surface water, groundwater interactions, and downstream transport of water, heat, and solids in a hydropeic river. He's working with Bayani Cardina, so please join us.
All right, hello everyone. I'm excited to present on our research, and the first presentation gave a nice background on the importance of studying surface water groundwater exchange processes that are influenced by hydropeaked operations. So moving on. All right, so this is the hydrograph 3 kilometers downstream from the dam we're studying. This is for the whole year of 2016, and you can see superimposed on top of big storm events, there's all these spikes, which are actually daily flood releases that result in 1 to 2 meter stage fluctuations near the dam and propagate downstream. To give you a more detailed look at these, this is about 2 months of hydropeaking operations at that same location. This is the lower Colorado River near Austin, Texas, by the way. And these are daily releases around the mid-afternoon during these 2 months. And to give you an idea of how dramatic these releases can be, this is a exposed sand and gravel bar in the morning. And in just a few hours, the discharge in this river will go from about 3 cubic meters per second to about 100 cubic meters per second and look like this temporarily. And this hydropeaking, as the first presentation nicely outlined, is not unique to this river. It's a global phenomenon, and this is a map of continuously and intermittently hydropeak dams across the United States. So this is something that affects hundreds of river locations and possibly tens of thousands of river kilometers downstream from these dammed rivers. The first observations in our river that piqued interest in surface water groundwater exchange processes were back in 2009. These are observations in stream from about 15 kilometers downstream from the dam, and you see daily meter stage fluctuations. And inversely correlated with those are fluctuations of specific conductance that oscillate between the surface water and groundwater end members. And that piqued interest in how is their infiltration during these hydropeaking events into the banks, and then the return flow from the banks and the resuming of groundwater inflow in the intermittent periods. And from that research, there was a conceptual model developed, the gill and lung model. The gill model is a gaining river that doesn't have hydropeaking conditions, so you have a restricted hyporheic zone in both the bed and the banks of the river, and unidirectional flow, whereas in a dammed river, you have these daily stage fluctuations that drive temporary gaining and losing conditions. You have an expanded hyporheic zone in both the banks and the bed of the river, and this inhaling and exhaling of water, like someone breathing, could have implications that expand the importance of the hyporheic zone in nutrient processing in these dammed rivers. And specifically for this presentation, we're going to be looking at a lot of data that looks at how these exchanges drive the movement of both heat and solutes into and out of the bank on a daily basis. The two main questions they were trying to answer were, how are the flow, thermal, and chemical regimes of the river affected by these daily releases? And also, how do these daily releases affect the conditions in the hyporheic zone of the bank and the bed of the river? And our approach to this was to not just look at one location, but to actually look at 4 locations in stream that recorded both pressure, temperature, and specific conductance during these dam releases. And also we installed 3 well transects at 3 different distances from the stream to look at the lateral movement of solutes, water, and heat in and out of the banks. So the first set of slides, these next set of slides are going to be presenting what the stream was experiencing during these hydropeaking releases. And then from there, I'll move on to what the groundwater was seeing. So this is 1 week of data in August 2016, and I'm going to be presenting the same week for all of the different parameters. The top plot is the hydrograph for that week, and you see there's meter to 2 meter stage fluctuations at 3 kilometers from the dam. And the way I'm going to be presenting this data so you guys can quickly see the patterns and how these dam releases manifest themselves are this heat map. So we have 24-hour period on the x-axis, and each one of these rectangles is a day. So here you can see those would be 4 representative days on the hydrograph, and on this heat map, they would correspond to these 4 days right there, with the heat map showing the stage fluctuation. So here are the 4 in-stream locations we had. They are progressively further from the dam. We have 3 kilometers, 15 kilometers, 35, and 80 kilometers. And then the stage fluctuations that correspond to those distances. So near the dam, you have large stage fluctuations, 1.5 meters, 2 meters. And as this dam release propagates, it attenuates. The size of the pulse itself diminishes, but the wavelength of it increases. So this kind of nicely highlights the driver of these surface water groundwater exchanges is dynamic in both space and time across this river, the river reach we're studying. The next set of data are, previously I showed how the stage is changing. This is actually how the temperature is changing during the same period in time. You can see near the dam, the temperatures are more muted, which isn't surprising. Interestingly, this is an epilimnitic dam, so the release itself is not very cool. It's 28 degrees, and the river in some areas experiences temperatures as high as 33 degrees Celsius at certain points of the day. And to give you an idea of the timing of these temperature patterns you're seeing and how they correspond to the flow changes and stage changes, the red boxes here show you where the stage changes were at these different reaches. And you can see that near the dam, they correlate with this muting of the peak temperatures in the afternoon. Further from the dam, they arrive in the evening, early morning times, and it's not clear if they're actually influencing, by this point, the temperature regime in these reaches. And lastly, we have the specific conductance, ranging from 500 microsiemens per centimeter to about 700. Near the dam, you see there's not very large fluctuations like we observed in that first plot I showed you early on. Those observations came from around this reach, 15 kilometers to the dam. And here you see this pattern of increase in specific conductance, arrival of the flood pulse, it decreases, and then the cycle repeats itself. Further from the dam, again, you don't see these dramatic changes you see close to it. I think this is a nice way of highlighting you want to have multiple distant observation points, because you might mischaracterize the system if you just look at one location and trying to extrapolate how the dam releases are affecting the entire river reach. So moving from these in-stream observations, I'm going to present some videos now that are showing how these dam releases are affecting the hyporheic zone in the bank. And to orient you, this is the area of the bank I'm showing. It's going to be the left side. And this top plot is going to be a video that's animating the stage changes. This is the hydrograph, and this is at the closest location we had to the dam, 15 kilometers downstream. This is a cross-section of the bank. This is the land surface. This is the river. These are groundwater levels based on 6 wells we have. And then beneath that is the temperature and specific conductance patterns. And to remind you, the specific conductance of the river is typically 500 to 600 microsiemens per centimeter, and the groundwater signature is closer to 1,000. So I think it's useful when you're looking at these to kind of look at each one of these plots individually, because it's a lot to take in. But you can see this daily basis. You have a rise in the river stage, which then creates a pressure propagation into the bank. And then you have the advection of both heat and also surface water into the bank. And the scale is quite large. Each one of these units is 2 meters. So you see this delayed appearance even 14 meters away from the bank of surface water signature. This is the same location. Instead of looking at the bank, this is actually in the riverbed itself. These are 5 wells that were spaced about 6 meters apart. This is a 25-meter width of the riverbed itself, and this is how the hyporheic water and also the specific conductance and temperature specifically responded to these dam releases. So you can see with the increase in stage, you have the lowering of specific conductance near the bank, so you have inflow of river water. Interestingly, far away from the river, 20 meters in the center of the river, when the pulse rises, you actually have the appearance of groundwater signature-specific conductance. And looking at the temperature response during the same period, you don't actually see a decrease in temperature here. So if you're only looking at one of these two parameters, you may not catch how spatially variable these responses can be. And this also may highlight how it's very difficult to make measurements, one measurement that would characterize this whole system. We're talking about putting measuring locations in the first presentation. There's challenges associated with that when you're trying to characterize these processes. This is 35 kilometers downstream from the release, again in the bank now. And this is the land surface, here's the river. And we'll see this switching between the gaining and losing conditions and the advection of river water and heat from the river into the bank. And the scale here is much smaller, this is 4 meters. But you can see again, this repeats itself on a daily process. And the scale here is again about 3 meters of movement into and out of the bank. And then lastly here, this is the furthest location downstream. The flood pulses themselves are much, much smaller here. They're just about 30 centimeters in amplitude. But still, even this 30 centimeter amplitude pulse is enough to cause there to be significant exchange between the river and the banks and the return flow. So kind of to summarize, to kind of give some illustration to that very general conceptual model in the beginning of the presentation, this is what our river system we hypothesized it would look like without dam regulation. You'd have a very restricted hyporheic zone in the banks in the bed of the river, and you'd have this general base flow condition occurring throughout the entire time. And these two images would depict where you'd expect to see surface water, specific conductance signatures, and also the heat from the river. And then under dam regulation, you see you have these alternating flow directions, and you have increased infiltration of surface water and heat energy into the banks. And having installed a lot of wells myself at those locations, there's a lot of gravel and sand lenses that can cause preferential flow that could lead to infiltration up to 10 meters into the bank. And in summary, our studies show that there is daily flow reversals and movement of surface water into the banks up to 80 kilometers downstream from the dam. Shows the importance of having multiple observation locations, both in the bank and in the river itself, to characterize how these conditions are changing as they propagate downstream. Also, the thermal and chemical influences could be much larger. Our dam is a very small dam. The releases are comparatively small compared to large hydroelectric power plants, and the releases don't have significantly different temperature than the ambient river water. And lastly, the implications for this increased exchange on the processing of nutrients, basically how the hyporheic zone has become expanded and much more significant in this dam-regulated regime. And that is everything. These are two posters related to this project as well that are being presented at the meeting.
Okay, thank you. We have one question. Jay, please.
So I was thinking about the lung model. You're showing us how the lung breathes, right? So if we're thinking about translating that to function, right? If you're a runner, you want to take breaths in certain ways to optimize oxygen intake in different cases. So maybe we're just updating your conceptual model here. Now you have how to optimize breathing in the lung to optimize for a particular function. What do you think?
Sure, yeah, and especially if you're thinking of the timing of when these releases occur, you could try to release so that you have higher maybe oxygen quantities in the water, or you time with the temperature to increase the function near the dam, because that's where you have the largest influence from these exchanges. But yeah, I think there's a lot of research that can be done, and also modeling to see if you change the release time or the release size, how you can have different responses to hyperextent function.
Okay, thank you. Now we're going to have a presentation on identifying stream water exchange by temperature gradient in a Guarani aquifer stream outcrop zone. And this is presented by Edson Wendland from the University of Sao Paulo, right? Correct.
So, good morning and thank you for the opportunity to show the work we are doing at the Guarani Aquifer System outcrop zone. I want to acknowledge the work by my colleagues, Davi Rosa, Jamil Anashi, who are students at the University of São Paulo, Chris Laurie from the University at Buffalo that has been helping us with this study, and Yufeng Lin from the University of Illinois. Since I'm not sure about the time, I will show you our conclusions, and then I will show you later how we got to this conclusion. So we could identify in the stretch that we study a base flux contribution between two flumes, estimated as 250 cubic meters per hour. The temperature gradients at the stream bed varied between 0.67 degrees centigrade per meter, which indicate recharge, groundwater recharge, also losing conditions for the stream, and 14.33 degrees centigrade per meter, what indicates a groundwater discharge condition. That means the stream is gaining water at these stretches. And the groundwater discharge velocities in the hyporheic zone is as large as 1 meter per day. So first I want to show you a little bit about the Guarani aquifer system. That's a huge sandstone that occurs among the 4 countries, Brazil, Paraguay, Argentina, and Uruguay. It has a total area of 1.2 million square kilometers, and as a reference, the state of Louisiana has an area of 135,000 square kilometers. So that gives you an idea of this aquifer system. Here's a cross-section of the aquifer system, the Guarani aquifer system here, and what we see is that the sandstone, which occurs in the outcrops, are represented as this blue layer here, and is covered by a huge basalt pocket. And the outcrop zones here are supposed to be the recharge zones of the aquifer. And there is supposed very few recharge through the basalt zones. So we are working on these outcrop zones, trying to understand how is the recharge in this aquifer and what is the amount and all the hydrogeological process occurring in the zones. I will be talking to you about the study we are doing in the Onça Creek Basin with an area of 65 square kilometers. Is essentially agricultural used basin. And we will talk about the study we have been doing in these spring areas here. On a distance of 1.5 kilometers, we installed 2 partial flumes to measure what is the base flow discharge. And here we got this information that we have a contribution behavior, that means groundwater discharge along the stream of 250 cubic meters per hour. And we want to identify if there are stretches of gaining condition and losing conditions. For this, we use the temperature as a tracer to identify these groundwater surface water interactions. And the idea is that we have a more or less constant temperature in the groundwater and a fluctuation temperature in the surface water. When we have gaining condition, groundwater discharge, the temperature sensor in the soil doesn't vary that much. In the opposite case, when we have losing condition, the temperature sensors in the soil indicate some variation, some fluctuation according to the surface water temperature. And we want to use this idea to identify stretches with gaining condition and losing conditions. The difference here is that in South America, normally we have a higher temperature in the groundwater, around 24 degrees centigrade, and a fluctuation temperature in the surface water between 16 and 24 degrees. So we have to do these studies when we have a larger temperature difference. For this, we installed a fiber optic distributed temperature sensing. It's a fiber optic cable installed on the stream bed along the distance of study. And we done a 40-hour heat mapping over a distance of 175 meters. We have a warm bed and cool bed to adjust, to control the measured temperatures. And what we get is this map, 40-hour map, heat map, along 2 days of monitoring over a distance of 175 meters. And the other side is symmetric because we have a U-band at the end. So, and what we identify is a variating temperature during the day, warmer temperatures during the night, colder temperatures is a cycle. We could identify the cycle, and we have stretches with warmer temperatures. That means that along this stretch we have groundwater discharging, and it could be identified all during this period. So the problem is only that we don't have exact information about the gradients. So we use the second methodology using a temperature stick with 4 sensors. This is just a bamboo with some sensors attached to it at distances of 10 centimeters. And the students walked along the stream measuring the temperature gradient in the bottom with this bamboo stick. And here's the idea. We have a temperature logger here, 4 sensors, one at the surface and a depth of differences of 10 centimeters. And when we have groundwater discharge, we will measure temperature differences more expanded. Warmer temperature of the groundwater, colder temperature of the surface water. On the other hand, when we have groundwater recharge, the temperature sensors have temperatures closer to each other. The cold water of the surface water influence the temperature in the soil. And these are the results that we got along the distance of 150 meters, according to the FODTS measurements. And we see some stretches with more compact temperature differences and some stretches with a larger temperature differences on the surface and a depth of the 30 centimeters. So, and this we identify as groundwater discharge stretches where the temperature differences are larger, and other stretches with smaller temperature differences, and these are recognized as groundwater recharge. So we see along the stream how this behavior changes, gaining stretches and losing stretches. The other measurement we have done is trying to identify how much groundwater is discharging or recharging depending on the temperature differences. And for that we installed 7 data loggers that monitor the temperature during a longer period, during 5 days. And we have 2 probes fixed on the stream bed with a difference of 20 centimeters. And we monitor the temperature variation in both sensors. So the result that we get is are curves like this, where we can see shifts in the temperature phase and temperature amplitude. And analyzing this data due to groundwater movement, upstream or downstream, we have a temperature convection. And due to the thermal resistance of the soil, we also have temperature conduction. And analyzing the shifts in temperature between both sensors, we can estimate what is the groundwater discharge or recharge. So, and here are the data we got for the 8 sensors. And at some sensors, we have a groundwater flux of 0.2 meters per day as discharge, or up to 1 meter per day as groundwater discharge, obtained through the temperature differences. And another stretch, we have groundwater recharge with a value up to 0.4 meters per day. And if we compare the quantitative measurements with the qualitative measurements that we have done with both different temperatures, we see there is a good concordance between the quantitative measurements for P1 and P2 data loggers with the obtained values in the previous measurement with the 4 sensor sticks. And it also combines here for the P3 logger that we see groundwater recharge behavior. We also have done this measurement with the temperature sticks along the whole stretch between both partial flumes. And these are the results we get. Along the distance of 1 kilometer, we have the sensor at the depths of 0, -10, -20, and -30 centimeters. And the warmer temperatures, or the spikes with a warmer temperature and colder temperature, indicate stretches where we have groundwater discharge. And here and the other points where we have colder temperatures, it indicates that we have groundwater recharge. So these are the gaining stretch, and losing stretch, and again gaining stretch and losing stretches. So my conclusions again, the base flux contribution between both flumes was estimated as 250 cubic meters per hour. Both the spatial and temperature variations could be monitored. The groundwater discharge and recharge stretch along the stream could be identified. The temperature gradients at the stream bed varied between 0.67 degrees centigrade per meter, what indicates groundwater recharge, and 14.33 degrees centigrade per meter, what indicates groundwater discharge. And the groundwater discharge velocity is as large as 1 meter per day. I want to thank you for your attention, especially for our financing. Thank you so much.
We have time for one question. Well, I have one question. How common it is that groundwater is warmer than surface water? I mean, it is just because this is a hydrothermal input, or?
Actually not. That's because we have a surface temperature. The mean temperature in the area is larger. So we don't have such much cooling at the surface, and the groundwater remains warmer. And during the winter, we have lower temperatures, up to 70 degrees centigrade, and that's the reason why the surface water is then colder than groundwater.
Okay. Thank you so much.
Thank you.
Yeah, don't be shy. Come on. Okay. Our next speaker is Michael Gratzer, and he is a graduate student at the University of Mississippi working with Greg Davidson. And the topic that he's presenting is identifying groundwater recharge from an Oxbow Lake wetland system based on hydrologic monitoring and temperature tracing. Welcome, Michael.
Thank you so much for being here for my presentation. Our study takes place at an oxbow lake in northern Humphreys County, Mississippi. This is an ancient oxbow of the Ohio River, the ancient Mississippi-Ohio River system. And the Sky Lake receives runoff from about a watershed of about 18.6 square kilometers of predominantly agricultural land. The surrounding forested wetland is up to a kilometer wide, mostly in the northeast part of the lake and then the southeast part of the oxbow, and it drains many ephemeral streams in the region. So our ultimate goal is to quantify the amount of recharge that's occurring from the lake to the aquifer. But really the scope of this project is to just use water level monitoring and temperature data to see if there's any evidence for significant recharge. And our hypothesis is that this recharge might be conveyed through preferential flow paths that are formed in the wetland sediments by the bald cypress tupelo forest that's very dense there. So to give some background on the Mississippi River Valley alluvial aquifer, this is a sand and gravel aquifer with an average thickness of about 30 meters, and it covers about 32,000 acres, 32,000 square miles, 83,000 square kilometers in the southeast. It's connected to many rivers and drains. It's mostly confined, but there are portions that are unconfined, and it's connected to aquifers beneath it as well as confining units. And the development that has been going on since the 1870s, but really the largest development increased around in the 1970s and then on from there, has decreased the outflow to the rivers. It's increased inflow from the rivers and increased inflow through the upper confining unit. It's a recent USGS study found that it's one of the most overdrawn aquifers in the country, and numerous oxbow lakes lie in the area overlying the aquifer. However, the relationship of the aquifer to any type of lake is generally unknown. Oops, I went backwards. So to inform our study, we collected 2 soil borings in the wetland to determine the thickness of the sediment above the aquifer. We also outfitted our 11 aquifer wells with pressure transducers to monitor the water level over time, and we're also monitoring surface water level in 3 locations. And then we're using vertical soil temperature profiles similar to the previous investigation, to actually quantify the flux rates in 10 locations in the wetland. So our soil borings, we found that there's at least 6 meters of fine-grained material overlying a transition to sand in the wetland. Regionally, from water levels measured in the Mississippi Delta region, we know that in our study area in northern Humphreys County, Mississippi, the hydraulic gradient is from east to west. And this is consistent with all of our water level measurements. These are measurements from March 15th. We see a general decrease in the hydraulic gradient as you move from up gradient of the oxbow to down gradient of the oxbow of about 410%, with our highest gradient down gradient of the oxbow of about 1.4 times 10 to the negative third. On April 23rd, we see similar pattern, a very flat potentiometric surface up gradient of the oxbow, and then it gets a lot steeper down gradient, about 490% greater, with a even higher maximum gradient in the northwest of the oxbow of about 0.0017. And then looking at the study area in June, we saw a 630% increase in hydraulic gradient moving from up gradient of the lake to down gradient of the lake with a maximum gradient of 1.4 times 10 to the negative third. And then just to give an idea for comparison, the lowest gradient is up gradient of the Oxbow in the area of SL8 of about 8.8 times 10 to the negative fifth. So now to look at some specific wells in our study area. This is the aquifer level in the wetland, and then this is comparing it to the head difference between the wetland groundwater and the surface water. And we see that every time the head difference increases, we also see a rise in the aquifer level, which is consistent with vertical recharge occurring from the wetland to the aquifer. Now to compare the well inside the wetland to one that's outside the wetland, but very close, only about 0.36 kilometers south. We see that there's definite muting in the water level rise. We're still seeing a rise each time that the surface water rises, but the amplitudes are much smaller for the well outside the wetland than the well within the wetland. And also the time at which the wetland well peaks occurs earlier after the surface water than the well outside the wetland. Now another well that's outside the wetland but still close, only about 0.4 kilometers south, 0.46 kilometers south. Here we're seeing, interestingly enough, a slightly higher amplitude in this earlier rise, and then a significantly higher amplitude for the later rise in June in water level. So the well outside the wetland is getting significantly higher water level rise, but it's lagged behind the surface water more than the well in the wetland. So, of course, we need to, there needs to be more data to determine whether these differences that we see are due to lithological differences, because of course we're definitely seeing a relationship between the surface water and the aquifer water, whether you're in the wetland or outside the wetland, but still we're seeing these differences in terms of lag times and the amount of rise. So there's definitely common influences, but we just need to better distinguish what's actually influencing these differences. And now just to look at a well that is about 1.28 kilometers south of the nearest wetland, you see almost no influence of the surface water. We do see minor rises that correspond to these, but almost unrecognizable. And so this just goes to show that the further you get away from the lake, the less influence there seems to be of the surface water on the groundwater. And then to talk about our vertical soil temperature profiles, we have 10 locations in the wetland with thermistors buried at 30 centimeters below ground and 60 centimeters below ground. And then we are measuring the surface soil temperature as well at one location. And with these, here I'm just showing two locations, location 1D and location 2E. They're about 15 kilometers apart. And this is just the 30 centimeter thermistors in both locations. And we can see that 2E shows a much more strong connection to the surface temperature in blue than 1D, evidenced by the steeper slopes of the rises and also the quicker peak times after the surface. Now looking at both locations at 60 centimeters below ground surface, it's lagged and muted, but we're still seeing a higher slope in location 2E, evidently more connected to the surface than location 1D. And we're using 1D Tempro, which is the graphical user interface for the USGS program VS2DH, which solves the advection dispersion equation for fluid transport and heat transport. So basically, we input the soil parameters in the wetland, as well as the temperatures that we've measured in a vertical profile, and then it simulates what the temperature would be at 30 centimeters based on our soil parameters and our surface and 60 centimeter temperature, and then it simulates the 30 centimeter temperature based on the flux rate and iteratively solves for what the flux rate is most likely. So this found a flux rate of 0.035 meters per day at location 1D, which is surprisingly high, so we still have to conduct some sensitivity analyses. But when we compare that to location 2E, it's almost double, which is what we would expect based on the graphical analysis of the temperature time series. And based on both the graphical analysis and the 1D Tempro, I conclude that these differences are due to a higher hydraulic conductivity at location 2E than 1D. And this might be due to the preferential flow paths that either are intersecting 2E or are just more abundant near 2E than 1D. So our preliminary conclusions are based on the hydrographs of wells close to the wetland versus a well that's farther from the wetland. We see a more close relationship to the surface water closer to the wetland, and this is consistent with vertical recharge. Secondly, we see steeper gradients up gradient of the oxbow than down gradient of the oxbow, and we hypothesize that this might be due to as the westward flowing groundwater goes beneath the lake and hits that downward flow, it's getting backed up, and that's slowing down the westward regional hydraulic gradient and leading to that flat surface at the top. And then finally, with our soil temperatures, we see variability in different locations, which is consistent with the spatial variability of the preferential flow paths. So our work that remains is to see if the patterns remain constant in our hydrographs in terms of distance from the wetland and response to surface water level, as well with our potentiometric surface, seeing if we're consistently seeing this flat surface up gradient and steeper surface down gradient. And then we're going to run more 1D Tempro simulations, hopefully get more accurate estimates of the flux and explore that variability there. So thank you so much.
Any questions for Michael? Yep.
Have you thought about measuring the surface conductivity near your temperature?
Actually, there was a previous study in the exact same area where they did measure conductivity, and they found variability there as well. They were looking at the redox potential at 30 centimeters and 60 centimeters, and what they found was that there were transient increases in redox potential that would suggest oxygenated water getting flushed down there periodically and increasing the redox potential. So this is sort of a follow-up to that to try to further explore it with temperature.
Okay, thank you, Michael.
Thank you.
The last speaker for this 2-hour block session, remember that we have 4 today. It's going to be Chao Wang, and he's going to present on the importance of capturing topographic features for modeling groundwater flow and transport in mountainous watersheds. Chao Wang is working with Jesus Gomez and John Wilson at New Mexico Tech. Welcome.
All right. So first, I want to thank our funding support from NSF and New Mexico Water Resources Research Institute. And so first, some brief introductory background. So the figure here shows that under the different recharge conditions, the change of the drainage density can have a significant influence on the groundwater flow path length, as shown here. So this may imply that capturing the streams in the model can have a significant influence on the groundwater surface water interaction. However, considering the computational the limitation of the computational capacity, it's seldom possible to capture all the streams in the model. And if we use coarse grid along the streams, the topography variability can be smoothed, and also the stream course can be distorted, as can be seen here. So with this, we want to see how the streams we missed in the model can influence the groundwater flow and transport. So we want to answer the following several questions. So is the simulated groundwater flow and transport pattern sensitive to capturing the key topographic features? So the key topographic features we are interested here include the streams and the ridges, and like one cross-section shown here. And this shows the typical topography-driven groundwater flow system with nested flow passes. And then how does capturing the key topographic features affect the simulated groundwater flow and transport? And third, what's the influence of geological heterogeneity on the above topographic effect? So to answer these questions, we use the mountainous watershed called Rio Hondo in northern New Mexico as an example. So we take an idealized system and assume a topographic controlled groundwater flow system by using land surface elevation as a specified water table top boundary condition. And the figure here shows the model configuration. So we simulated the 3D fully saturated steady state groundwater flow and mean age. And based on the mean age, we also estimated the solute concentration from subsurface chemical weathering. And we run models with different topographic complexity levels. And we use the different hydraulic conductivity profile to represent the geological heterogeneity. So in order to see the effect of capturing key topographic features, we build models with different topographic complexity level. So we first capturing streams only, and this figure shows, for example, we first captures the streams of the two highest orders, and we progressively capture more lower order streams until we capture all the streams in the model. And for each of these topographic complexity level, we further captured the ridges with the corresponding order. And so the order numbered complexity levels only capture the streams, and the even numbered complexity levels capture both streams and ridges with same orders. And the most complex model captures all the streams and ridges and was used as a reference model to evaluate all the other model scenarios. So this just shows very quickly the effect of capturing more lower order streams, so we get more finer grade along lower topographic features. So we used different hydraulic conductivity profile to represent the geological condition. We have one homogeneous case and 6 exponentially depth decaying hydraulic conductivity profile. So for the hydraulic conductivity profile, which decays slower, it can represent the system with fractured and permeable bedrock. So the water from both shallow and deeper flow paths can contribute significantly to the stream base flow. And for the case which hydraulic conductivity decays very fast, the system is only dominated by the water from shallow flow passes. With this model configuration, we run the model and we simulated the flow rate of the base flow and the mean age and estimated the solute concentration of one representative solute from subsurface chemical weathering. And with this matrix, we calculated the relative difference for each of these matrices between the model of reduced topographic complexity level and the reference model. And the calculation is done for all the streams in the domain, no matter if it's refined in the model or not. And the results is summarized in terms of this kind of box plot. So you're going to see a bunch of this kind of box plot later. So it basically shows the relative difference for each reduced topographic complexity level model compared to the most complex model, complexity level 8. And each of these plots shows results for stream reaches of one certain order, because we have many stream reaches of one certain order, so it's summarized in terms of this kind of box plot. So first, let's look at the effect on the flow rate. So this figure shows the relative difference of each model of different topographic complexity level and for streams of different orders. So generally, we can see here, if the model doesn't capture the lower order topographic features, the base flow into the lower order streams is biased lower, but the base flow into higher order streams is biased higher. So it means if the lower order topographic streams is not captured in the model, we will get more flow through those longer regional scale groundwater flow passes into the high order streams, and less water through those shallow and local scale flow passes into the lower order streams. And so these plots are for the case with slowly decaying hydraulic conductivity. And if the hydraulic conductivity decays fast, we can see the general pattern actually is similar, but the magnitude of the relative difference is enhanced. So it means if the flow is forced to be in the shallow part of the system, the effect of topographic complexity can be more significant. So now is the result for the mean age. So again, it's still the relative difference, and the axis means the same thing, but for the matrix of mean age. So we can see now the mean age of base flow into all the streams are biased higher. So actually, this is consistent with the result for the base flow, if you still remember, because we have less water flows through shallow and local flow passes, and more water flows through longer and regional flow passes. So we have less younger water and more older water. So the water into all streams, they are biased older. And if we have a faster decaying hydraulic conductivity, we can see again the relative difference. The magnitude of the relative difference is increases. And so if you still remember, the even number topographic complexity level captures only streams, and the odd number, the even number that captures both streams and ridges. We can see capturing ridges doesn't make much difference. So now is the comparison for the solid transport. So the solid for the solid concentration. So the solid concentration is estimated using a very simple geochemical model. So basically, it's a function of the Dam-Holland number, which is the ratio of the fluid travel time to the time for reaching chemical equilibrium for the subsurface chemical weathering. Absolutely, this is consistent with the result for the mean age. So when the mean age is biased older, the water stays in the subsurface for the longer time, so it gets more chemically evolved, so the solid concentration is biased higher. And then, if we look at the case with faster decaying hydraulic conductivity, we can see now it's different. Now we can see the effect of topographic complexity is diminished by the fast decaying hydraulic conductivity profile. So to see why, I plotted the relative difference versus the decaying rate of the hydraulic conductivity. So this represents the effect of topographic complexity. So we can see when the decaying rate increases, but it decays slowly, the effect of the topographic complexity actually is enhanced. But as we further increase the decaying rate of the hydraulic conductivity, the effect of the topographic complexity is diminished. So this is because overall here, the system has lower hydraulic conductivity, so the mean age of the so the solid subsurface chemical weathering of the system is constrained by the time for reaching chemical equilibrium, because now the mean age is longer. And for the high order streams, because it's always mostly gets water from longer flow passes, so the water always has a longer mean age. So it gets chemically evolved, and the effect of topographic complexity is minimal. So with this, we conclude that capturing streams is fundamental for reproducing the groundwater flow and transport characteristics in the mountainous watersheds, and capturing ridges doesn't make much difference compared to capturing streams. And the effect of topographic complexity can be influenced by the heterogeneity of hydraulic conductivity and also by the reaction kinetics for solids from subsurface chemical weathering. And all these implies that all these have implications for interpreting the environmental tracer and geochemical information, and also predicting the hydrological and the biogeochemical response of stream waters in mountainous watersheds. Thank you for listening, and with this I will take any of your questions.
Questions, please.
Your investigation focuses especially on the planimetric view of the channel network. Have you also explored the channel network profiles, so the archimetric profiles of the channels, and the importance that these profiles have in the groundwater surface water interaction?
Oh, thank you. So actually, it's not only focused on the planetary view of the channel network. So because it's a 3D model, so when we refine the measure along the model, actually we capture the 3D topography profile of the 3D topography profile along the streams. And I think here the important thing is we capture the local topography variability just near those streams by refining the model along the selected stream and the ridge features. So thank you.
At the back, there is a question.
So you use a steady state model.
Yes.
The system is inherently not in steady state. What do you think would happen if you actually incorporated some of the seasonal dynamics, where you have high recharge seasons, then you have relatively low recharge seasons, say winter and summer events?
So yeah, this is a good question. So actually we have had some considerations, but because so this simple model using steady state condition actually gives us some indication of the system. But if I want to see the like the transient state, actually because for the model I want to capture the topography variability. So the model is already, even for the simplest case model, is already very dense. So and so you can I didn't say, but I use hydrogeosphere, so it can definitely simulate the Vandal zone and the transient condition. But for the for this kind of very big model, it's just very hard to get the results for the transient case. And I think if we simulate the transient case, we will get more interesting results. As we can see in the introductory background, and with the recharge change, we can see the dynamic of the discharge zone. And I think the capturing those topographic variability can give us some more interesting results. That's my expect, kind of. Thank you.
Jay, one more question? Jay?
So if you talk about playing around with different characteristic landscape river network morphologies and looking at whether or not you sort of have patterns with sort of representative elementary volume analysis, because we see the pattern that you have there, right? Small orders have all the variability, and whether or not you have high-low, basically baseball conditions, or if your network is changing in shape or flow, that variability is going to move up and down also, right?
Yes, yes.
So have you thought about that and how you're going to inform our community?
Actually, yeah, so like for a simple case like if the hypsometric curve is different for the system, we may see different effect of capturing those topographic features. So actually, this is like a primary step of my work. Now I'm looking at how the structure of the topography and the channel network actually is influencing the groundwater flow and the transport pattern. It's still an ongoing work, so I hope I can present it later.
Okay, great. I think we have to stop here so people have time to go to the restroom and come back here in 20 minutes, because we're going to have the chemical, the biological, and other ways of looking at groundwater, surface water interaction. So please come back. Thank you.